Hi, my name is Solvi Arnold and I will present our work on affordance-based planning. Our goal in this work is to realize open-goal multi-step action planning for visual domains. Traditionally, action planning often employs symbolic state descriptions and action rules. However, symbolic approaches tend to be brittle and limited by the imagination of the system designer. How so? Say we have a rule that placing object A on object B results in A being on top of B. This sounds sensible enough, right? However, this rule is actually quite brittle. Take this case here. Is A going to be on top of B after this action? Probably not. To determine what the actual effects of an action will be, we really need fine, granular state representations. Our approach uses affordances to structure the problem space, but predicts their effects using a granular learned prediction model. Hence, our system combines affordance recognition and effect prediction. By affordance recognition, we mean finding the actions available to the robot in a given state. We modify a recent YOLO iteration to recognize affordances instead of objects. By effect prediction, we mean predicting the result of executing a given affordance in a given state. We implement this as an extension of our own EM*D network architecture. This network predicts result states as images. So now we can find the affordances in the task space, predict their results, and, key point of our strategy, because predictions are images again, we can apply affordance recognition again to find the affordances in predicted future states. This mechanism allows us to expand the tree of possible futures. We expand this tree up to a given depth, and for each predicted state, check its agreement with the goal. Once we know the state with the best goal agreement, we return the affordance sequence leading to that state as our action plan. By batching parallel branches, we can process thousands of future states in seconds on a GPU. To evaluate the system, we constructed a tabletop manipulation environment in Unity. The environment contains some cups, balls, and blocks for the robot to manipulate. The action repertoire consists of grasps, placements, and 90-degree turns. The setup is pretty basic, but you see a variety of interactions between objects producing complex affordance effects. We generate random experience data in this environment for training the recognition and prediction networks. Then we constructed a set of 27 test tasks spread over 9 task types. Tasks take 2 to 4 actions to solve and require consideration of factors such as action order, target obstruction, stability of placements, and interactions between objects. The system gets one shot to solve each task without any additional task-specific learning. Let me show you a few examples. In this task, the robot should put the red ball on the left gray block. However, gripper access to the ball is obstructed by the surrounding blocks. To clear the goal, the system first rotates the colored block out of the way to access the ball, then moves the ball to its goal position, and then restores the block to its original orientation. So here we are executing one affordance to make another affordance available. Because predictions are images, the system can also present an intuitive visualization of its plan ahead of execution. This task is a bit of a trap. The robot has to place the cup on the right side of the block. However, the right side of the block is not supported, and placing the cup on it would cause the block to tilt over and the cup to fall off. The system foresees this pitfall. It first moves the block into a position where the right side is supported by a gray block, and then safely places the cup on top. Here we need to put objects on both ends of the block, but only one side is properly supported. Solving this requires the use of counterbalance. We must first place the object that goes onto the supported side of the block. This weighs down the block, making it possible to place the second object on the unsupported side. And here is a task with a negative goal. By changing the planning logic a slight bit, we can plan to avoid or eliminate what's depicted in the goal image. The task here is to eliminate the blue cup from the scene. There are no affordances for that particular purpose, but the system figures out how to make it happen anyway by exploiting non-canonical effects. You can check out the video attachment to our paper for examples of all task types. Overall, we obtained a success rate of 25 out of 27 on our set of test cases, showing that our system can plan effectively on this task domain, avoiding and exploiting non-canonical affordance effects as necessary without task-specific training. Planning time varies with the branching factor of the plan tree, but is a few seconds for all tasks in our set. Since the paper, we've implemented a few new extensions. One extension is language integration. Specifying goals as images is impractical in practice. By integrating a clip model into our setup, we have made it possible to specify goals using text. We've also integrated the system with robot hardware. Using a domain adaptation approach, we can solve similar tasks in a physical setup. Alright, thank you for watching.